Hi, my name is Madi and this is Lab 5, Design Your Own Adventure for a Falling Slinky at Georgia Tech for Physics 2211. This lab measures a slinky's motion from being expanded and then dropped from rest. The observed motion of this object will be measured and compared to a computational model. Different forces affect an object's position. The results show that more forces taken into account creates a more accurate representation of the slinky, which can be obtained as the observed model ended with the position negative 1.792 meters in the y component, and the predicted model ended with the position of negative 1.794 meters in the y component. In order to look at motion, Newton's second law is needed. This law states that a force is applied on the system when there are interactions between objects, and all these interactions can be added up to be equal to one net force, which can be measured as the change in momentum over change in time. In this lab, the slinky is being dropped from rest since the initial velocity of the object is 0 and then speeds up. This indicates that there is acceleration and a non-zero net force due to the momentum principle. One of the forces that is well aware is gravity, or the force of Earth on the object. The gravitational force is proportional to the object's mass and has a specific constant known as Earth's gravitational constant of 9.8 meters per second squared. This constant comes from the gravitational law. When multiplied by the opposite of direction vector, and the gravitational force on the object can be calculated. This number is in the negative y direction, since the object is falling towards the Earth. The atmosphere is made of many particles, and these particles will have interactions with falling objects. These interactions result in drag forces. From the previous lab, drag force was specified as being proportional to the square of an object's speed times proportionality constant. The drag force will be pushing against the rolling object, so the value needs to be in the opposite direction as the velocity vector. Since the slinky is being expanded, the last thing that needs to be considered is the force of the slinky it has on the bottom of the slinky. When the object is dropped, the tension is still the same in the respective from the bottom. So the slinky will not move until the top of the slinky has reached the bottom. With these three forces added together, the net force on the slinky can be calculated using the tracker motion from the video on the next slide. The object falling from rest was able to be measured. The center of the mass of the object is indicated by the red dot in each frame as it moves in the negative y direction. The corresponding table and graph show the relationship of position versus time. As shown from the slow motion video, the bottom of the slinky remains motionless as the tension force equals and opposites to the gravitational force, just as it was at rest, so the bottom of the slinky was chosen to analyze this type of motion. The mass on the object was 0.5 kilograms, estimated by the average metal slinky, and the initial position of the object is located at 3.1 times 10 to the 9 meters, and the x component at negative 1.286 meters, and the y component, the amount of time it takes for the slinky to reach the ground, is 1.714 seconds, and since the object is being dropped from rest, the initial velocity is 0 meters per second in all components. As the velocity of the object increases, it is proven that there are forces interacting on the object. In the glow script code used to predict the motion of the falling slinky, the initial values from the observation are put in place, such as mass, position, velocity, gravitational acceleration constant, and the direction of the forces. And the B component for drag force was determined to be 2.6. The first while loop times indicated to represent when the bottom slinky was motionless. The forces interacting with the object during this time is just the gravitational tension forces, which are equal but opposite to each other. The velocity was updated from Newton's second law, and the updated position formula was also written into my code. In the second while loop, the time was indicated to represent when the bottom slinky was in motion. The forces interacting with the object during this time are the gravitational and drag forces, as indicated during the fundamental principles, and the velocity and position update formulas were also written in my code. The results show that the predicted and observed values were super similar, except for a few discrepancies. Once objects started falling, this could be due to the fact that the slinky may have continued forces acting upon itself. It was originally analyzed that the table slinky came in contact with the final slinky as it continued to fall as one, but there could still be tension and other factors contributing to the fall of the slinky. In the future, I would try to analyze both the top and bottom parts of the slinky and not just the bottom part to see if the velocity changes with contact or if additional forces need to be included overall. Thank you.